Alrighty, welcome to today's presentation. Today we will be going over an introduction to computer vision. And here are the topics for today. Alrighty, so what is computer vision? Computer vision is an interdisciplinary field that deals with how computers can be made to gain high-level understanding from digital images or videos. And pretty much what this means is that it gives the computer the ability to extract useful information from an image. And in the bottom left and bottom right, you can see examples of this. So why is computer vision used? So again, computer vision lets computers understand visual data. And with this understanding, computers can automate complex tasks that could previously only be done by humans. And our robotics team is using computer vision so that the rover can understand the world around itself and drive autonomously to target locations. So what are some types of computer vision? So first of all, we have object detection and object classification. So in the top right, you can see animals being detected and also classified by their type. We also have image segmentation, which we saw previously. So in the bottom left right here, image segmentation, where the computer understands where an object begins and where an object ends in a space. We have scene reconstruction and 3D scanning. So pretty much with this, you're able to take for example, there are applications where you can take multiple photos of an object, and this will be converted into a 3D mesh, which then you can use in some type of 3D software. And then also there's motion tracking, which we'll be talking about in a few slides, and pose estimation, which you can see an example of with this golfer, where the computer is estimating the position and orientation of the golfer's arms, body, and legs. All right, so what are some real-world uses for computer vision? So, one example, facial recognition. So, a lot of phones in the present day have the ability to unlock using a facial scan, and this is computer vision. It's using an algorithm to scan your face and detect that it is you. Also, self-driving cars. So self-driving cars have many different sensors, but also cameras. And with these, it's able to detect what specific objects are around it. So it can detect if there is a person, or if it's a car that's beside it or in front of it, or a tree. Also, we have robotic automation, medical anomaly detection, sports performance analysis, manufacturing fault detection. So in a factory, if let's say a product has been damaged on its way through production, a computer can catch this damage and notify someone that it has happened, or it could automatically be put in a place for damaged products that will not be finishing production. And then we have agricultural monitoring, plant species classification, which we previously talked about classification, yeah, and text parsing or optical character recognition. So for example, when you go to scan a document with your phone and it gets converted to a PDF, this is what it's doing. It's parsing the image for text, and it's converting that to text that the computer can understand. So what types of computer vision will our team be using? So 3 main types of computer vision that we will be using are motion tracking, pose estimation, and object detection. So a common programming library for computer vision applications is OpenCV, and we are currently using this library. We're using it because it's open source, it's supported on multiple platforms, and it is fairly easy to use. And so on the left here, you can see what we're using for pose estimation and object detection. So pretty much these are called Aruka markers or Aruka tags. And then on the right, we're using motion tracking with VSLAM, which is Visual Simultaneous Localization and Mapping. And these will be explained in the next couple slides. So, Visual Simultaneous Localization and Mapping, or VSLAM. So pretty much what this is a type of motion tracking and mapping. So what does this give us? So this pretty much gives us odometry, which is a change in position over time. So pretty much we'll have an understanding of the position and orientation of the camera that's attached to the rover. And also it gives us mapping, so we'll have an understanding, and the computer will have an understanding of where the camera is and has been in 3D space. Also, with this information, the rover will have information about where it has already driven and will have the ability to backtrack when necessary. And so this would be in its autonomous navigation plan. All right, and then Aruka markers. So Aruka markers are a type of AR tag. And what is an AR tag? So it's pretty much a type of tracking marker that's used in computer vision applications, and they're specifically made so that they're easily recognizable by a computer, or by, I guess, through the camera to a computer. So yeah, by a computer. So what information does this give? It gives position and orientation information of an object in 3D space. And in our usage for the autonomy mission, these markers will be placed throughout the desert, and the rover will have the ability to detect these markers and drive to them. And then using computer vision algorithms, we will not only know the position and orientation of the markers, but also know an estimated distance from them. And that's how we're going to be able to drive to them and not crash into them, because we will know our distance from them. And that's it. But before we go, we actually have a demo of Aruka detection. So I'll boot this up. And if I hold up these Aruka tags, you can see that using a computer vision algorithm that one of our members created, or a script that's actually using OpenCV, it's able to detect the position and orientation of these tags. So you can see the red, blue, and green in the center of each tag. You can see the orientation and position. But also you can see that in addition to this, we actually have an estimated distance from each tag to the camera. And this distance is not actually accurate right now because the algorithm is not calibrated for this specific camera. But once calibrated, it will be a better estimation. Alrighty, and that's about it. Thank you.